Alright, so today we want to continue with our lesson on the binary number system. And today we've gotten to how images are represented in binary. We want to learn how the computer stores images.
When you see an image on your screen, what you are really looking at are millions of tiny units called pixels, which are individually colored and make up the entirety of your screen. Now let's suppose that your screen was made up of a simple 8x8 pixel grid. If we were to color your screen with only two colors, then we could use 0 to represent white and 1 to represent black. And we can store all the information we need to form the image on your screen using just ones and zeros. Now if we were to increase the amount of colors on our screen, then we would need to increase the number of bits used to represent colors. So in general, how many colors and bits do we need? Well, one of the most commonly used mappings is the RGB color model. RGB stands for red, green and blue, and the color of each pixel is the result of the additive effect of these three colors, which is stored as a 24-bit integer, with the first 8 bits representing the amount of red, and following that the amount of green and blue. Now for a binary string of 8 digits, we can store up to 256 distinct integer values, which means that for 256 possibilities for red, green and blue each, we will have a total of over 16 million possible colors for each pixel. And so in order to form the image on your screen, your computer passes 24 bits at a time from the image file and colors each pixel accordingly. It does so for all the pixels in the image, and that's it. That's how an image in your computer is represented by ones and zeros.
Now, we have learnt in binary that the images we see on our screen are all binary codes. And this is something amazing that we want to get some insight into. So, as part of our studies in binary, we need to understand how images are stored in binary. So over here, our subtopic says representing images in binary. Computers store images in binary codes. The question is, how does computers store images in binary codes? How can images we see be in binary? And as a matter of fact, even our videos are just binary codes. How? After you understand how images are stored in binary, understanding how videos work will be easy for you, because all videos are images. If you are using a video camera to capture anything, it is just pictures that are being taken. And if you have studied a little bit about how videos work, you realize that videos use at least 24 pictures per second to make videos. Every second there are 24 pictures that are captured. If you want to experiment this, just take your still camera and let somebody be walking and take as many pictures as you can of the person walking. Then put the pictures next to each other and play the pictures. You'll see that the person is moving in your pictures. That is how videos are made. All that video cameras do is to take several pictures per second, and they take between 24 to 30 and sometimes a little bit more. So right now, I think most cameras are taking 30 pictures per second. And it's so interesting. So videos take pictures, and so when we understand how images are stored, we can understand exactly how videos are also stored. Videos use millions and millions of binary codes to make videos. Now, any image displayed on a computer screen, depending on its quality, is actually lots of binary codes being interpreted as several dots of colors to form that image. It says that any image you see on a computer, depending on the quality, is actually lots of binary codes being interpreted as dots of colors to form that image. What it's simply saying is that on computers, images are simply dots that are colored. If you check the picture here, you can see several boxes. With this picture, we have zoomed in a little because of the studies for you to see the dots very well. And those dots are the boxes you see. If you see these boxes, you can see that these boxes are just colored boxes. These boxes are just colored boxes. If you go closer, you will see that they are just colored boxes. Can you see that they are colored boxes? They are just colored boxes. When you zoom out, all those colors come together to form the image. This is exactly how all images are formed on computers. There are several boxes or several dots, we call them dots, that come together to form the image. And each of those dots is colored with one color. Now, when you look here, you can see that each of the boxes here have one color. This one has one color, this has a different color, this has a different color, this has a different color. They are all having colors. When you come out, all the colors together form the beautiful image. The technical name for these dots is what is called pixel. Each dot is a pixel. Pixel stands for picture element. What then are pixels? In digital images, a pixel, also known as a dot of a picture or picture element, is the smallest controllable element of a bitmap image represented on a screen. Every image on a screen is made up of many small dots that form the image. So to understand how computers store images, this is a sentence you need to understand. Every image on a computer screen is made up of many small dots. This is the only secret about how computers store images. Every image is just the arrangement of several dots, thousands and even millions of dots. And each of those dots is colored. So you need to understand that pictures are made this way. And any picture at all you see on a screen is this way. To prove it, I have opened 3 different pictures here. Please, you see these pictures? To you, they are pictures, right? Hello? To the computer, these are not pictures. These are just millions of dots that are put next to each other. And each dot has a specific color. But for us, we see a beautiful image, right? Let me prove to you that this image is made up of dots. You can only see under a microscope. What I would do is to zoom in, zoom way in. And when we get too close into this image, you see that the image will turn into boxes or dots or pixels. Let's start with this one here. We can zoom into any portion of the image. Already, do you see some boxes? Please, are you seeing these boxes? I don't know if you can see, but I see them clearly. These boxes form the image. If you can see, this is one box. Can you see the shape of one box here? This is it. This entire picture is made up of these boxes. And all the computer has to do is to color each box. Each box. Now, the computer has a color code for each box. And the color codes for each box are represented in numbers. So those numbers are the data the computer stores. And those numbers are stored as binary codes. Before the computer colors this particular box, it needs an information about the colors that make up this box. And what will amaze you is that just this box here, the computer mixes 3 different colors in different proportions to form each box. And the computer uses 24 bits of binary code to create just one box. The reason why it is using 24 bits is that it is the 24 bits that will give the computer the ability to generate any color it wants. And so because the computer has access to 24 bits, it can actually color this box well. And when it is done coloring all the boxes, they'll be put together and they will look like a real photograph. If a computer is not having 24 bits, it can try shading them, but it will not get the perfect colors to use. And so this image will end up in a different color. That doesn't look realistic to the human eye. When you see a picture in black and white, you know that it is not in full color. So there's an issue about the number of colors used to make that image. That is what happens when the computer doesn't have all the 24 bits. Let's try another image and see. This image here is a beautiful Indian lady. Let's zoom into any part of the face and let's see. When you go inside, when you go in, please, are you seeing the boxes? This image is only made up of boxes. And all the computer needs to do is to shade each box with a perfect color. To get a perfect color, the computer needs 24 bits of binary code. Because if the computer has 24 bits of binary code, it can get the perfect color it needs for each box. When you look at the eye, it's very, very obvious, right? There are several boxes. So, to form images, first of all, it's all about shading and coloring each box. Now we'll get into how the colorings are done and how the computer gets those colors. That will be the next thing to discuss. To color those pixels or boxes, the computer uses a color model called RGB. Please, are you with me? The computer uses a color model called what? RGB is a color model that stands for red, green, and what? Blue. In digital electronics, these 3 colors are known as the primary colors in digital electronics. When it comes to electronics and screens, digital screens, these are the three colors that are called primary colors. Now, in real life, we also have primary colors in real life. And if you ask for the definition of primary colors, you'll be told that primary colors are colors that are not obtained from the mixture of any other color. They are natural colors. When we talk about primary colors, what the definition is that primary colors are colors that are not obtained from the mixture of any other color. They are natural colors. The second thing you learn about primary colors is that all other colors that exist are created by mixing these three primary colors in different proportions or quantities. Think of any color. That color you think about was created from the three primary colors that exist in real life. The three primary colors that exist in human life are red, yellow, blue. Those are our primary colors. In computing, we have different primary colors, slightly different primary colors. And these primary colors here, they are red, green, and blue. To experiment this, you can just sprinkle a small drop of water on your phone screen or on your laptop screen, and inside the water, inside the sprinkle of that water, you are going to see three colors appear in, if you've never seen that already. On my screen, if I sprinkle, I'm not saying pour water on your screen. If I sprinkle a tiny drop of water on my screen, the water on my screen will reflect three colors. I'll see red, I'll see green, and I'll see blue. Those are the three primary colors for computing or electronics. Now, what we are telling you here is that every color, every other color is created from the mixture of these three colors. When you mix red and green, you get a certain color. When you mix blue and green, you get a certain color. When you mix red, green, blue in different quantities, you get different colors, and out of the mixture of this, you are going to get over 16 million colors. Over 16 million colors. Just by mixing these three colors, you are going to get over 16 million colors. Now, in computing, each color has a level. The lowest level of each color is 0, and the highest level of each color is what? 255. So red has 0 to 255, green has 0 to 255, and blue has 0 to what? 255. Every color that exists in this world is made up of an amount of red, an amount of green, an amount of blue. Do you see these three numbers I have put here? These three numbers represent one color. What I'm simply saying is that mix 20 levels of red with 50 levels of what? Green, and 28 levels of what? Blue. Instead of using comma, let me just space them out like this. This is a color, what you see. Even though I've written numbers, it is a color. This color here, let me prove the color I have just written here to you. I'll go back into this program and draw a shape. This shape, I want to color it. For the start, let me just give it any color at all before I start. I'm now about to start. I'm going to prove the color I gave you. Now, in this particular program, I'm allowed to choose a color model I want to use. Right now, what do you see here? CMYK. I'm not going to use CMYK. I'm going to use the RGB color model. Please, are you here? Now, watch this. Watch this carefully. The color you are seeing here, have you seen the definition of those colors? R is what? G is what? And B is what? The color I gave you, I said R was what? 20. G is what? 50. And B is what? 20. 28. When I finish, that is the color I have produced here. It looks like navy green, military green. This is like military green. So this military green here is made up of these three numbers. Please, are you seeing these three numbers? Yeah. These are the three numbers that make up the colors. So what you need to understand is that colors are numbers. You just need to provide three different sets of numbers. The first number represents the amount of R, which is red. The second number represents the amount of green. And the third number represents the amount of what? Blue. Watch this. I can raise this thing way up. And the last point gives me what? 255. Have you seen this? Now, this is 255. That means a lot of red. Let me remove every green. I can bring green to 0. When there's red and there's no green, let me bring blue to 0. I get pure red. Have you seen this? Now, let me take all of red and add all of blue to it. I'm going to get something like purple. When I mix red and blue, I'll get purple. If I reduce the amount of red to, let's say, 150, and I reduce the amount of blue to 150, I also have purple, but a purple in a different shade of purple. So it all depends on the amount of colors that we have in. If I add some green to the purple I have, then the color is changing. Can you see that it's changing? Wow. I've added a lot of green. I'll see how it's looking now. So what you need to understand about computing is that all colors are made up of three numbers. All colors are made up of what? So what the computer needs to do is just to shade each pixel with three numbers. Because those three numbers gives the computer the color for that pixel. Hello. So very soon I'm going to give you more information about the three numbers and how those three numbers can be converted in binary. But before I say that, I want to tell you something that fascinates me a lot. It blows my mind. I've always been thinking about it, but it blows my mind all the time. Please, are you here? Do you see the color we are seeing here? If I increase the red to the fullest red, which is what? 255. There's something that always shocks me. Watch this. Red in its full amount. If I add green in its full amount, and I add blue in its full amount, look at the color I'm getting. Which color is this? White. This is so shocking because inside white, all those three colors exist inside white in their fullest amount. So white is actually a color that has all colors within it. This is something that blows my mind. And I know that it is generating white because these three colors are actually lights. And when you put these three lights together, you get pure white. When you remove all the colors, when you remove all of them, guess what you will get? Pure black. So black is the absence of color or light. Darkness is the absence of light. When light comes in, the darkness disappears. And so white is an amazing color that has all colors. Black simply means no color at all. When there's no color at all, you get pitch black. But when there is color, black goes away, and when color increases and all the three colors increases in their full amount, we get white. This is what blows my mind. I'm yet to understand this very, very well. I know these lights will give you white. I know that, but it still shocks me all the time. Now, let me try and explain let me fix my navy green and then we will go ahead. So R is what? 20. G is what? 50. And B is what? 28. So I'll click OK, and that's the color we have here. That is it. Now, from this explanation, I want you to know that every color is made up of three different numbers. Three different numbers. The first number represents the amount of R. The second number represents the amount of what? G. And the third number represents the amount of what? Does that make sense to you? The next thing to understand is that each number here can be converted into 8 bits of binary codes. For example, when you convert 20 into binary and you are supposed to use 8 bits, we have learned that binary is always in 8 bits, right? Okay, this is the ones position, this is the fourth position. So the fourth position, I'll give it 1. This is the 8th position. This is the 16th position, I'll give it 1. Sorry, so we have ones position, twos position, this is a twos position, this is a fourth position, this is a 8th position, this is a 16th position. So the binary code for 20 is what you are saying here. This is a binary code for 20. So this particular 20 will be stored as this. 50, how will 50 be stored? We have learned binary already. So let me just explain 50. We know that this is a ones position, this is a twos position, this is fourth position, this is 8th position, this is 16th position, this is 32 position. 32 will be part of 50, 16 will also be part of 50. 32 plus 16 will be what? 48. So now we need 1 from the twos position and we have 50. This is a binary code for 50. 28. This is a ones position, this is a twos position, this is a fourth position, this is a 8th position, this is a 16th position. 16th position will have 1, 8th position will have 1. 8 plus 16 is what? 24, right? Then the fourth position will also have 1. That'll be 28. This is a binary code for 28. If you want us to prove this, let's prove it with the division method. We remember our division method. In the division method, you ask yourself, how many times does 2 go into 20? 10 times, remainder 0. How many times does 2 go into 10? 5 times, remainder 0. How many times does 2 go into 5? 2 times, remainder 1. How many times does 2 go into 2? 1 time, remainder 0. How many times does 2 go into 1? 0 times, remainder 1. So the binary code for 20 is equal to 10100 because you read from the bottom upwards, right? Now you are asked to leave your answer in 8 bits. So to leave your answer in 8 bits, bring 3 zeros in front, because what we have here are 5 bits. 1, 2, 3, 4, 5. 5 bits. So to leave my answer in 8 bits, I'll bring 3 zeros first. Then I'll enter 10100. It's the same thing. Please, do you understand? Check the number we have here and compare it to what we got here. Is it the same? Is it the same? Good. So that's 20. Let's convert 50 and see. 50, if you convert it with the division method, how many times will 2 go into 50? 25, remainder. How many times will 2 go into 25? Remainder. How many times will 2 go into 12? Remainder. How many times will 2 go into 6? Remainder. How many times will 2 go into 3? Remainder 1. How many times will 2 go into 1? 0, remainder 1. So 50 will give us, reading from the bottom, we'll get 110010. How many bits do we have? 6 bits. So we'll bring 2 zeros in front. 110010. Let me compare and see if we had the same thing before. Check. Are they the same? This, is it the same as this? Is it the same? So you can use the positions method to get your answer. Let's try that for the last one. 28. 20. How many times will 2 go into 28? Remainder. How many times will 2 go into 14? Remainder 0. How many times will 2 go into 7? Remainder 1. How many times will 2 go into 3? How many times will 2 go into 1? 0, remainder. So 28 should give us 11100. How many bits? 5 bits. So to make it 8 bits, we'll have 000111100. Let's compare this to what we got here. Are they the same? Are they the same? That means with the positions method, you can also know your binary code like we did before. Now, count the number of bits we have here in all. Do you know that this is 8? 8 bits, right? 8 plus 8 is what? 16 plus 8 is what? 24. So in all, the computer uses 24 bits to be able to generate any color. If you give the computer 24 bits, the computer can generate any color for you. The reason is this. The reason is this. Let me show you the reason. Let me put it here. The lowest value for each color is what? 0, right? 0 in 8 bits is simply 000000000. That's the lowest color you can get. So when you give the computer 8 bits and there is no color, this is what it will return. It is still in 8 bits. Now 255 in binary. 255 in binary. Do you know what it is? It is 1111111. This is the highest binary code you ever get in 8 bits. The highest binary code you ever get in 8 bits. That means if you give 8 bits to the computer can form the lowest color possible, and it can also form the highest color possible. And so it needs 8 bits for each color to be able to pick any color it wants from the lowest to the highest. So out of these 8 bits, it can create from 0 to 255. Out of these 8 bits, it can create 0 to 255 of green. Out of these 8 bits, it can create 0 to 255 of blue. And out of these 8 bits, it can create 0 to 255 of what? Red. So this particular binary code you are seeing here, please, are you seeing this binary code? This is a color. 24 bits, it is a color. So all the computer will do is to use the whole 24 bits to color one of the dots. So this dot here, you see the dot here, is made up of 24 bits. So the computer continues and colors each color, each box, and colors each pixel. The computer colors each pixel with 24 bits. So this particular image, do you know how many pixels we have forming this image? Let me go and check. I have the image right here. If I want to know, I will right click and go to the properties. When I go to the properties and I go to details, they are going to tell me how many pixels make that image. The width of the image is made up of 607 pixels. And the height of the image is made up of what? 711 pixels. We are talking about dots, right? Multiply this 607 by 711. If you do this multiplication, (607) times 711. That picture you saw is made up of 431,577 pixels. Are you with me? These are the number of boxes used to construct this image. Remember, this image is just made up of boxes that are put next to each other, and some below and on top. This is full of boxes, and each box has a color. The total boxes for this image, we have discovered it. The total boxes for this image are 431,577 boxes or pixels or dots. Each dot is made up of 24 bits. Each dot is made up of 24 bits of binary code. When you multiply this whole thing by 24, this picture uses over 10 million bits of binary codes to form this image.
Hi, my name is Lamore Freed, and I'm an engineer here at Adafruit Industries. And this is where I do engineering and design, and I design circuits for fashion and music and technology.
My name is Federico Gomez Suarez, and I'm a software developer with Microsoft Hack for Good. And I look into using technology to help us solve some of the big social problems of our times.
You may have heard that computers work on ones and zeros. Or you may have seen scary looking visuals like this. But almost nobody today actually deals directly with these ones and zeros. But ones and zeros do play a big role in how computers work on the inside.
Inside a computer are electric wires and circuits that carry all the information in a computer. How do you store or represent information using electricity?
Well, if you have a single wire with electricity flowing through it, the signal can either be on or off. That's not a lot of choices, but it's a really important start. With one wire, we can represent a yes or a no, true or false, a 1 or a 0, or anything else with only 2 options. This on-off state of a single wire is called a bit, and it's the smallest piece of information a computer can store. If you use more wires, you get more bits. More ones and zeros, with more bits, you can represent more complex information. But to understand that, we need to learn about something called the binary number system.
In the decimal number system, we have 10 digits from 0 to 9, and that's how we've all learned to count. In the binary number system, we only have 2 digits, 0 and 1. With these 2 digits, we can count up to any number. Here's how this works. In the decimal number system we're all used to, each position in a number has a different value. There's the 1 position, the 10 position, the 100 position, and so on. For example, a 9 in the 100 position is a 900. In binary, each position also carries a value, but instead of multiplying by 10 each time, we multiply by 2. So there's the 1's position, the 2's position, the 4's position, the 8's position, and so on. For example, the number 9 in binary is 1001. To calculate the value, we add 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Almost nobody does this math because computers do it for us. What's important is that any number can be represented with only 1s and 0s, or by a bunch of wires that are on or off. The more wires you use, the larger the numbers you can store.
With 8 wires, you can store numbers between 0 and 255. That's 8 ones. With just 32 wires, you can store all the way from 0 to over 4 billion. Using the binary number system, you can represent any number you like. But what about other types of information, like text, images, or sound? It turns out that all these things can also be represented with numbers. Think of all the letters in the alphabet. You could assign a number to each letter. A could be 1, B could be 2, and so on. You can then represent any word or paragraph as a sequence of numbers. And as we saw, these numbers can be stored as on or off electrical signals. Every word you see on every web page or your phone is represented using a system like this. Now, let's consider photos, videos, and all the graphics you see on a screen. All of these images are made out of teeny dots called pixels, and each pixel has a color. Each of the colors can be represented with numbers. When you consider that a typical image has millions of these pixels, and a typical video shows 30 images per second, now we're talking about a lot of data here.
Every sound is basically a series of vibrations in the air. Vibrations can be represented graphically as a waveform. Any point on this waveform can be represented by a number. And this way, any sound can be broken down into a series of numbers. If you want higher quality sound, you would pick 32-bit audio over 8-bit audio. More bits means a higher range of numbers.
When you use a computer to write code or make your own app, you're not dealing directly with these ones and zeros, but you will be dealing with images or sound or video. So if you want to understand how computers work on the inside, it all comes down to these simple ones and zeros and the electrical signals in the circuits behind them. They are the backbone of how all computers input, store, process, and output information.
Let me recap. Every image on a computer is just made up of boxes or dots. Each dot is colored with 3 colors. Each dot is colored with 3 colors. The 3 colors are RGB, red, green, and blue. And each dot has a specific composition of red, green, and blue. The composition of the first dot is different from the composition of the second dot. Each dot has its own composition. The color for this part is different from the color for this part, but they are all 24 bits. just that the numbers in the 24-bit are different, and the numbers represent the levels of the colors. Please, are you with me? This is exactly how images are formed on your computers. Let me read what is in the notes and we'll wrap up. I like this here. Listen to this. It said early computers used only 4 bits color for each pixel of images. When computers started, they used 4 bits to color each dot. Do you know what will happen if you use just 4 bits to color each dot? What will happen? The picture will not be clear. It won't have true color. With 4 bits, you only have about 16 possible colors to choose from. That's not enough to be able to give each pixel the true color it needs. That's not enough. Are you with me? But if you have 24 bits, you have over 16 million possible colors. That means any color you need for each pixel, you can get. And when you finish coloring the pixels, you are going to get the image in its true color, because you have all the 24 bits to use. So watch this. Early computers used 4-bit color per pixel for images, providing a maximum of how many colors? 16 colors. Imagine you have only 16 colors to choose from. You can't do much. This was a start, but 8-bit color per pixel proved much more interesting, allowing 256 colors. So computers upgraded from 4-bit to 8-bit, and with the 8-bit we had 256 colors to choose from. As computer hardware improved, the number of bits per pixel, keep that in mind, per pixel increased to 16-bit. A time came we were operating in 16-bit. We were having color, but the color we were getting was not true color. 16 bits will give you 65,000 colors. Now watch this. And then eventually we moved to the 24 bits, which gave us over 60 million colors per pixel. And it makes a lot of sense for us to operate in 24 bits because we know binary operates in chunks of 8 bits. So if R has 8 bits and G has 8 bits and B has 8 bits, 8 plus 8 plus 8 is what? 24. It makes a lot of sense. Look at this image. This image was constructed with just 1 bit. Do you know that the possible number of colors you get with 1 bit? You only get 2 colors, either black or white. So imagine you have just 2 colors to form a picture. You try your best to get a picture, but it will be in pure black and white. This is not even in grayscale. This is pure black and white. They have done well to be able to use just black and white to construct this parrot. Do you see that as a parrot? Okay, if I hadn't told you, you may not have seen it. Let's see what they did next. When they got 4 bits, 16 colors, they were able to use 16 colors to produce this parrot. They tried their best, right? But does it look real, like in true color? Because 16 bits are not enough for each pixel. Then they got 8 bits. This is how 8 bits produced it. Then they got 16 bits. 16 bits is a little bit close to true color, but it's not. It is only 24 bits that will give you the image in true human color. So we now operate with 24 bits. If you have 24 bits, imagine this is the picture you are supposed to color, and you are a computer, and you only have 16 colors to choose from. You cannot color each pixel with the exact color you need. But with 24 bits, you can provide each pixel with the exact color you need, and the image will come out perfectly. Perfectly. Hello. So 24 bits is what computers use to form images in true color. And this is very interesting and explains how images are stored. In a nutshell, once again, for computers to store images in binary, computers break the images into millions of pixels. It separates the images into pieces of pixels, and it treats each pixel individually. When it gets to each pixel, it uses 3 numbers to represent the color that makes up the pixel, because each pixel is exactly one shade of color. And each color is made up of 3 numbers because of the RGB color model. The first number is a number for R, the second number is a number for G, and the third number is a number for what? For B. These numbers can then be converted into binary easily. If you have a decimal number and they ask you to convert to binary, it's very easy. And the binary code or the binary conversions are stored for that pixel. So the next time the computer needs to form this image, the computer will trace all the pixels, bring their 24-bit binary code and color them. Move to the next pixel and color. 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 It will do that till the entire image is drawn with color. So this picture you are seeing here, it is made up of colors placed next to each other in small dots, tiny dots. Each pixel is made up of 3 different numbers. Okay, each of those numbers, when each of those numbers are stored in binary, they are stored as 8 bits. So 8 bits will be stored for each number. For R, the number for R, 8 bits will be stored for the number of what? G, and 8 bits will be stored for the number of what? B. So when you add the 8 plus 8 plus 8, what do you get? So the reason why we say they are 24 bits is simply because 8 belongs to R, 8 belongs to G, and 8 belongs to what? B. Now when you are given binary code in 8 bits, you can easily convert it to a number. Any binary code given to you can be converted to a number. Now those numbers, when you come and you find out the colors that make up those numbers, you will find out that no matter the number you have, that number represents a color. So let's say this is one of our pixels, and we want to color this pixel. Let me open to the coloring box and we will see how we will color this our pixel. Okay, so I have my color box here. Give me the number for each color. R is what? Just give me any number. 30. Do you know that 30 can be stored as 8 bits in binary? Yes. Give me the number for G. It can be between 0 and 255. So give me any number. Give me a higher number. A higher number. Let's use 170. And give me a number for B. 200. So these numbers you've given me, this is the color you get. You see this color? The computer will pick these 3 colors, these 3 numbers, and produce one color. You see this color we are getting? That is the color for that pixel we are talking about. So this is just one pixel. What we just did, the computer will do for all the pixels it finds. So each pixel has 3 different numbers. This particular pixel, we said it's a pixel, right? Let's assume this is a pixel. Let's check the numbers that make this pixel. I'm bringing you down here. Have you seen the numbers here? R is what? R is what? And G is what? And B is what? These are the numbers that make a color, this color. So 3 numbers all the time will make a color. 3 numbers will make a color because of RGB. If 1 is 0, it will still make a color. 0 is still a number. And we told you that the levels are from 0 to 255. So even 0 is a number. Just that you can't go beyond 255. If you make any of them 0, it is still a number. And we'll still get a color for that. So these particular 3 numbers, this is a color gotten from these 3 numbers. What it means is that we are mixing colors. We are mixing 30 amount of R with 170 amount of green with 200 amount of red. Just mix them together. This is the color you produce. If you like, try it in real life. Just fetch a level of R from a paint and put it on a palette. Fetch a lot of green, and fetch a lot of blue and mix them together. This is a color you can end up with. So we are doing color mixing.
So that's 1 pixel.
Just 1 pixel. And these 3 colors are just for these 3 numbers are just for this color for just 1 pixel. And what we are saying is that these numbers, each of them will be stored as 8 bits. So this will be stored as 8 bits. This will be stored as what? 8 bit. This will be stored as what? 8 bit. Those 8 plus 8 plus 8 put together will be what? 24 bits. So the computer uses 24 bits to form each pixel. The computer needs 24 bits. When you give the computer 24 bits, it will give you each pixel. But one thing about the 24 bits is that it can produce any color it wants. And so if it goes through each pixel producing the best colors, by the time it is done, the image looks correct to the human eye in true color. That is how the computer can form any image. So the secret here is that, let's study this picture here. You realize that each pixel is one particular color. You see that the pixel is a shade. Each pixel is not having 2 colors mixed. It's just 1 color. This is just 1 color. If you study them very well, each pixel is just 1 shade of color. Each pixel is not made up of a gradient. There's no gradient anywhere. If you think there's a gradient, you are wrong. It is just 1 color in each pixel. Just 1 color. So these colors are placed next to each other, and each color is made up of 24 bits. Placed next to each other, can you see boxes of colors? This is how all images are formed. When you come out, then it will look like a picture to you as a human being. But when you are within, you don't know that it's a picture. You are just coloring the boxes. That is what the computer does to draw pictures for us. It just does coloring of boxes. And we see a beautiful image at the end. Because the boxes are very tiny that when they come together, they form a picture that we can't even tell. Unless you zoom in, or use a microscope before you can tell. This is exactly how images are stored in binary. So if you want to understand how computers store images in binary, that is what we have explained. And if a computer is given binary code and the computer is asked to construct an image out of the binary code, it's going to be very easy for the computer. Let's say we have millions of binary codes given to the computer. We have millions of binary codes given to the computer, and the computer is told that what you are seeing is a picture. Draw the picture for me. The computer will say, oh, easy. You know what the computer will do? The computer will separate them into 24 bits. All the computer will do is to make sure that it will separate the code into 24. Then out of this 24, you know what it will do? it will separate them into 888. 8. Eight. You see? Now the first 8 is the color for R, the number for R. This is the number for G and the number for B. The computer will put these 3 numbers together and get the color for one box. So if you give the computer a lot of binary codes and you say that it's an image, the computer will say, oh, simple. It will just take 24 bits and do coloring. Color them, boxes, color next to each other, and when it's done, you will see your picture. So when you have a picture and you store the picture as binary, this is all the computer stores as your picture. If you store a picture on a pen drive, this is what you are actually storing. You are storing zeros and ones. If you want to see your picture again, the computer will take the zeros and one and create the picture for you, because it can create it. All it needs is a color codes for each pixel, and it will do it. This is a digital world. Any picture you take will become an input in digits. So we are in a digital world. Any image you capture, you have just captured a lot of ones and zeros. So when I capture you, you are converted from human being to ones and zeros. That is how the computer can recreate you on the screen. And all of this happens in just a blink of an eye. When I capture your picture, I've stored your binary code. Alright. So I want to thank you for making time for this lesson. This is a very important lesson, and I'm happy we've been able to go through it. If you have any question, I want you to leave it in the comment box below, and I will answer you. If you need more explanations, let me know. And if you want more lessons from this channel, I want you to subscribe, like, comment, and share with your friends. So thank you for joining us, and I'll see you in the next video. Bye.